In this lesson, we're going to take a look at the flip side of the coin of residual radiation compared to the prompt radiation that we spoke about for the last couple lessons. So now, what is residual radiation? Well, residual radiation is anything that is not classified as prompt radiation coming from our nuclear weapon. So, for the most part, residual radiation is from our fission fragments. Now, there's some other stuff that comes at late times from activation via neutrons or excitation via gammas that we see that don't really contribute to that prompt source term that we looked at previously and can be lumped into this delayed or residual radiation component. It's mostly about timing. Now, when I talk about residual radiation, it doesn't necessarily mean fallout, as the title of this slide would suggest. Residual radiation, again, is any radiation that comes after a certain point in time from a nuclear weapon detonation. Now, residual radiation, most of what we consider residual radiation can and does come in the form of radioactive fallout. And this is any of the isotope species that we've created via the fission fragments or activation or what else have you, where it is in a vapor state in the radioactive cloud. Think of the top of the mushroom cloud, and over time, this stuff resolidifies and ends up coming back down out of the cloud. If our burst is close enough to the ground, what we end up with is a lot of basically soil and anything that was on the ground being pulled up or entrained into the detonation. And this stuff can be completely vaporized or partially vaporized, and it can interact with the radioactive material from our weapon itself, which sticks to it or gets caught within it as it recoalesces and then falls out to the ground. So what we're looking at here this is from the infamous Castle Bravo test, where the yield estimate was very far off. So it was much more, it had a much higher yield than they had anticipated. It had to do with lithium isotopes, and one they didn't really think was going to contribute, but it ended up doing so. Now, once we've got this radioactive cloud at the top of, our typical mushroom cloud picture that we, have in our heads for a nuclear detonation, right? So immediately following the creation of this radioactive cloud and all the stuff that's been pulled up into it and vaporized and half vaporized and whatnot, any of the real heavy stuff, that wasn't completely vaporized, that's going to fall out down to the ground very quickly. And some radioactive material may get stuck to it because that stuff may still be in a vaporized form. But this is like rocks and things that weren't vaporized from the ground. Stuff gets stuck to them, they immediately fall back down. And we can see that when we look at the residual radiation has its highest point directly at ground zero. So this is, again, stuff collecting radioactive material from the cloud and immediately falling down. Now, as we start to look outwards, the radioactive cloud at the top of our mushroom configuration, over time is, if there's any kind of ambient, wind or other atmospheric effects, it's going to move. So it's going to move, and then it could spread out in both horizontal and so both horizontal planes. So this way as well as this way. So it can spread out and be moved, and that's what we're seeing with this contour map of where did the large parts of the radioactive material that were contained within the cloud, where did they end up precipitating out? So we can see that on the island of Bikini, we have a highest point right here at ground zero. Our second highest point is just slightly past that at 3,400. But then as we look to the areas where perhaps the wind wasn't moving the cloud or the wind was pushing in an opposite direction, we see a very rapid fall off here towards the southern end of that island. But now as we look out, we have these very large contours where we have 3,000, 1,300 down to 100, and 3,000 contour line pretty much overlaps with this atoll, which was apparently where the cloud actually moved. And here we see, again, some very high numbers of, 3,300, 1900, 2700, and this would depend on, maybe there were some geologic features of the island, or maybe there was some atmospheric conditions that made it more prevalent for our radioactive material to precipitate out of the cloud at these particular areas. But again, if we look at this atoll, which was technically probably closer, it wasn't really within the cloud that was carrying all this material's range, and so we see very, comparatively low radioactive fallout numbers here. Now, when I say radioactive fallout numbers, what do I mean? Well, this is dose in terms of rad. Well, it doesn't say what kind of rad. Remember, we talked about rad silicon and rad carbon and rad tissue. It doesn't specify, but let's go ahead. It assumes rad tissue. So what we find out is relatively lower amounts of rads here, and very low amounts out here. By this time, I would suspect that the cloud had pretty much dissipated, and most of the material that had been entrained had already fell out of the cloud, and that's why we get these really high numbers right here. If we move a little bit further outwards, we see them start to drop, and again, the more south we are from the ground zero, where the cloud didn't really get to, we see even lower numbers. So what does all this mean? Well, it means our fallout, our residual radiation, is heavily affected by weather patterns. And the residual radiation, being compared to fallout may not necessarily be the same thing. And I can give you a for instance where some residual radiation that's created doesn't necessarily take the form of any kind of fallout. And that would be any of the gaseous fission products that comes out. Xenon, I'm trying to think of any of the noble gases. Xenon being one of the ultimate indicators that a nuclear fission event occurred. We use it now for detecting clandestine radioactive tests. But any of these gaseous materials or gaseous isotopes, they're part of the residual radiation, but they're not necessarily fallout. So just kind of a counter example of why these things aren't necessarily the same. But for the most part, we can say, yeah, they're close enough. Okay, so let's talk about the residual radiation coming off of our nuclear weapon. Now, I said it's mostly fission fragments, and it really is. I would say a huge portion, probably 90% of all the radiation is coming from our fission fragments. So we talked about some units before. We talked about becquerels, disintegrations per second. We talked about curies, which is 3.7 times 10 to the 10th. Becquerels or disintegrations per second. But now let's go even higher. A megacurie is obviously a million curies, so that's 10 to the 16th radioactive particles, if you will, emitted per second, or radioactive decays per second. Now, why do we have to go all the way up to megacuries? Well, when we talk about residual radiation per kiloton at 1 hour following our detonation, we have, just gamma alone, we have 530 megacuries. And this is such a stupidly high number. You have no frame of reference for something at 10 to the 16th. It's just such a large amount of radiation. The word inconceivable actually pops into mind. So 530 disintegrations per second, megacuries at 1 hour, that corresponds to 2 times 10 to the 19th almost radioactive disintegrations occurring per second. This is just an absolutely insane number, and the amount of radiation that's being produced here is just, again, there really is no frame of reference to understand how much radiation this is. Now, this radiation is not from single decays. Okay, there are many of the isotopes that are created as fission fragments that undergo rapid decays in a chain-like fashion. And so what we see here is fission pair fragments. We have lanthanum 144, and we have krypton 90. Again, it's one of those noble gases. like xenon that is created. So not necessarily part of fallout, but we look at their decay chains. Actually, this one was bromine 90, which then went to krypton 90. And then we see rubidium, strontium. I don't know if that's yttrium. I think Y is yttrium. And then all the way down to zirconium. And then over here we have lanthanum going to cerium, to promethium, to, I think that's, I don't know what ND is off the top of my head. I apologize. And then we end up here at stable cerium. So every time we see one of these things in this decay chain, each one of those is contributing to this this residual radiation. And a lot of the fission fragments do undergo several subsequent decays in order to reach a ground state to where they're considered stable. Okay, so it's not necessarily just all of this stuff decaying at the same time. If you look through these decay chains and what the different decay times are, or their half-lives, we can see that the residual radiation can be very intense early on, or it could be very longer half-lives. It can be very minimal early on, but then we'll see it building up over time as we rip through these short decay chains until we reach a saturation point and we're building up something that's much longer lived. But we'll have a whole lot more of it, and then it can be potentially much more dangerous in the long term. So these decay chains become very important, and to get an idea of the timescales involved, you really have to go through and look at what are all these daughter and granddaughter products, how long do they last, and how much are they contributing to this residual dose that we're going to see. Now again, looking, this is very similar to what you've seen before. This is our fission fragment distribution. They're slightly different depending on which nuclei we're talking about. So here we have plutonium-239, very common in weapons. Uranium-235, also very common in weapons. And then uranium-238, which is present in some weapons. And it will fission if you throw a high enough energy neutron at it, instead of turning into plutonium-239. But what we can see really is that these are pretty much the same. They vary just slightly. So we look at where these things are and what percentage of the fission yields are we looking at. So we see here, this is 100%. This is 1%. So if we look up here, this represents about the 60% line. And we're going to see things that isotopes that fall in these areas be more prevalent than anywhere else. We see a dip here in the middle, and that's because we would have to have two isotopes that were really within this little dip together so that their mass balance equaled out. And then we see some real outliers here where we have really light nuclei and really heavy nuclei. Now it can happen, the split distribution, for our mass, but generally speaking, it tends to, again, about 60% occur in these two plateaus here. Now, let's look at how things move with time. Now, we have gamma distribution on the right-hand side, or basically what kind of gamma emissions are we seeing about 96 hours or 4 days after detonation. And then we have this other one right here, which is looking at beta activity. In very long term, it goes all the way out to 10,000 days. So let's look at the gamma. So what this is saying is, and I think this is from a plutonium. I think this is from plutonium fission. I'm not absolutely sure. What I do know is it's not a classified figure. So what we're seeing here is that 96 hours following fission, we see most of the activity is down in these lower ranges. That's not necessarily because the isotopes that are being produced, although that's what these singular looking lines are. We can match these lines to very specific decays of different isotopes. So we have, 200 or so keV lines. This is probably about 300, 300 to 400, 500 coming here. And so when you see these very thin lines, these are very specific isotopes. But all of this stuff, some of this stuff is basically high energy gamma scattering down into the lower energy regime, so that we really can't tell, what they came from. I mean, there are techniques for determining, what contributed what portion. But anytime we see a line, we can say we can match it to an isotope, and then we can do some nuclear forensics to get some more information about what we're seeing. But a lot of this stuff we're seeing is probably it's below 1 MeV photon range. However, we do see stuff at the higher end that does come out 4 days after our detonation occurred, and this stuff is we could be pretty concerned about. Because it can go on and do a lot of nasty ionization interactions. We're really concerned about the low end too, because of that photoelectric absorption. Within our cellular biology, which could be hugely detrimental to us. So we have some super high energy stuff. Most of it's contained under 1 MeV. And again, this is 4 days, and we should see this start to subside over time, depending on which isotopes are producing these gammas. Now, here if we look at the beta emission, beta emission is important because it's a transitory state for an excited nucleus. So when we have radioactive decay of some nuclei, they undergo beta decay to turn into some other element, some other nuclei. And if we look at the tops of these curves here, and this has all the different isotopes that correspond to all these curves, you can, if you want to take time and sort it out, feel free to do so, but it's here more for illustrative purposes, is that some of these curves, they peak very early on in time. So lanthanum 140, barium, radioactive iodine. But then once we start moving down here, we start to see that the curves spread out and don't peak until much later. Until finally, if we look all the way over here, 1,000 days out to 10,000 days, we're seeing these very late peaks. And this corresponds to what I was referring to earlier, which are these decay chains. So we start with these radioactive unstable fission fragments. They can undergo multiple decays, and the buildup, basically, of these elements where these peaks are, is determined by which one of these is the longest lived out of this entire decay chain, because we won't see them very early on. The shorter stuff is going to dominate. But as you move forward in time, this stuff's going to start to build up and build up and build up until it reaches the point to where now it's built up to pretty much its maximum value, and now it's just going to decay away. And that's what we can see here. And if we look at these two lines here, strontium and yttrium-90, that's this curve right here. And then the next curve up looks like cesium-117. Actually, that should be cesium-137, sorry. They're not even peaked yet. So what we can infer from this is, strontium-90, yttrium-90, if that is yttrium, I assume it is, and cesium-137 live so long that they still at 10,000 days, which is years, they still haven't peaked out yet. So these are probably going to be some of the more dangerous of this fallout in terms of interactions long past when the nuclear detonation has occurred. They tend to stick around for a very long time. And cesium-137, it emits somewhere right around here. Actually, this is probably the cesium line, 662 keV. And cesium is bad because it can be mistaken for, I think, calcium by chemical processes, so it can be uptaken where calcium would normally see. Same with, I think, strontium is very similar. It's something called a bone seeker. So radioactive strontium tends to collect in your skeletal structures. So both of these are very, very bad in terms of long-term effects on people. Okay. So cluttered diagram. We'll go through it here a little bit at a time. And the reference here is where you could find it should you be interested in. So what is this showing us? Well, this is basically showing us how much stuff are we basically picking up with our nuclear detonations in terms of scaled height of burst and in terms of yield itself. So if we look at the y-axis, this is a log axis. Actually, this is a log chart. So this says anhydrous mass loading at 10 minutes. And this is megaton stuff. It's called dust here. Megaton stuff picked up per megaton yield. So megatons as in, physical measurement of dirt that got thrown up into the atmosphere per megaton of yield. So it's a direct correlation. If we have 1 kiloton, then we're going to see 1 kiloton of junk thrown up into the atmosphere. Okay, and then we look here. This is scaled height of burst. Hopefully by now you really understand scaled height of burst. So let's take a look here. If we look at scaled height of burst, there comes a point where we're not producing a crater anymore because we've moved up high enough for a burst to not really be picking up a whole lot of material to create a giant crater like we would see with a subsurface burst with Sedan. If we go way down to scale height of burst in one, I mean some of these numbers are subsurface bursts. So we can see the end of cratering right about here. A little bit less than 10-foot scaled height of burst. We see that we see ejecta here falling out. We have this term sweep up. This is again stuff we're pulling up into the radioactive cloud. We have this estimated upper and lower bounds for the total amount of junk that we see in terms again of scaled heights of burst and yields. And then we have this middle line here, which is kind of the average. So as we start moving outward with our scaled height of burst, once we hit about 100, now the fireball is not even going to touch the ground. So we're going to do a lot less of this sweeping up the stuff that was on the ground. And then finally, when we get all the way up towards 1,000 scaled height of burst, we're way too far up, so nothing is really interacting with the ground. So we're not pulling any of this dust and dirt and particulate matter up into our explosion. So what does all this mean? Well, this means the lower your height of burst, the more junk you're pulling up into your radioactive cloud, the more it's going to interact with the radioactive material that you've produced from your detonation. So the more volume of stuff that's going to fall back out. And again, in addition, we can have activation of certain types of elements that may be contained within whatever dirt and dust that we're pulling up. So you can increase the amount of radioactive fallout simply by pulling more stuff up to where it can interact readily with the radiation that we already have present within the cloud. But our scaled height of burst is really telling us the big takeaway from this one is where do we really end cratering? Where do we end contact with our fireball from the surface? And then finally, when can we expect to not see any interaction between our detonation and the ground? So particulate formation. This is the stuff we actually see, that we actually think of when we think about fallout, which is radioactive bits, dirt, things like that. So we can see here at t equals 0 seconds, soil and fission products, this is stuff that we are absolutely vaporizing in the very early stages of our detonation. Once we get some cooling going on around 20 to 25 seconds, we're at about 3,000 K. And now some of the things that we vaporized, including some of the stuff in the soil and some of the fission products, they're going to start coming together, but they're not really quite creating solid material at this particular point. Looking a little bit further on, we see our temperature dropping down to about 1600 degrees Kelvin. And now we're creating these aggregate materials. Well, kind of. So we're creating aggregate materials, but we're also taking and condensing out the stuff that we vaporized previously, which is turning back into whatever its normal state happens to be. We still have fission products that are maintained within our radioactive cloud. But now we're starting to see stuff form together, and it's going to start coming out of the cloud. And then around 30 seconds to a minute, our temperatures dropped out into 1,000 Kelvin. And then we start to see more of our material coming out of the cloud. We're starting to see the formation of aggregates, which is basically we have different lumps of material which aren't quite cooled down all the way yet, so they can stick together. So instead of seeing smooth singular volumes of this fallout material, what we can see is stuff. And there's a picture in Glassstone and Dolan where it looks like a bunch of these things have formed, and then they've all kind of stuck together on their way down. So another picture out of Glassstone and Dolan on page 412, it shows two different types of radioactive fallout. And if we look at the figures here on the right, these are photographs of cross sections of these materials following a nuclear detonation, and they look very different. So we look at the top one; it's almost perfectly spherical. It's got kind of a uniform structure to it, and this would be something. This would be material and whatever radioactive material and the stuff that had been vaporized from the ground. This is coalescing from completely vaporized material into a sphere, and that's surface tension being what it is, sort of a natural formation for vaporized material as it starts to coalesce. If we look at the bottom one, super irregular, doesn't look like the top picture, and this is more indicative of something that never completely vaporized. So a chunk of rock that got really hot, right? And so it may have had some melting on the surface, but it didn't vaporize altogether. And so looks like you would expect a rock to look, and not like a sphere. Now, if we look at the two pictures on the right-hand side, what we're seeing is something called autoradiography images. And this is just, they took that cross-section that we see on the left-hand side, and they put it on some radioactive sensitive film. In this case, it was most likely film. And the radiation interacted with the film so they can get an idea of where the radioactive material was concentrated, right? Because it's going to darken the film more where the radioactive material is located. So in this particular case, for our spherical one, we see that pretty much the radioactive material is distributed very evenly throughout the entire body of our hemisphere here, or our partial sphere. And this should make sense because as this vaporized material comes together, it's not really picking and choosing where it's going to, the radioactive material from our weapon is going to entrain into it or be distributed throughout as it's forming. So it should be uniform distribution. Now, the irregularly shaped, the rock, as I'll call it, we see that the radioactive material it's pretty much confined to the surface of this particular piece of fallout. And again, this is something that didn't vaporize, but it might have gotten hot enough to melt like the outer surface is. Once it becomes, we'll call that the sticky phase. Once it becomes sticky, then the radioactive material from our weapon detonation can then, basically coat the surface of it. It won't find its way into the inside because it didn't vaporize, but there's enough of it to where we can see that very clearly the outer surface of this piece of fallout is where all of the radioactive material located itself. So the top one, totally vaporized, came together, the probably silicates in the ground that was pulled up. So this is basically like a glass bead that has a uniform distribution or mixture of radioactive material inside of it. And then we have a rock that didn't vaporize, but the outside of it got hot enough to be sticky to other materials. They coated the outside of it, and it produces what we see here. Okay, so here's a figure. This is just showing in terms of yield in kilotons, basically how big is our cloud going to be, the radius of our cloud, and how high is it going to get. And what we can see is that, as we increase in yield, our cloud radius jumps up exponentially. And then not so much with the height of the cloud, There's actually a limitation to how high a cloud can be before it goes exoatmospheric. And this is one of the limitations to weapon yields in general. If your weapon yield is big enough, it stops producing effects after a certain point, because most of the explosive energy gets funneled up and kind of out of the atmosphere. So as we go up in yield, we go up in cloud radius exponentially until, again, we hit that upper level, that upper limit. And then the height of our cloud increases pretty linearly right up until we get into the 10 megaton range. And then moving a little bit up from there, we have, this is 30 megatons. The biggest one, of course, the US, I think, ever did was the Castle Bravo test. We do know that the Soviets tested one at 50 megatons, the so-called Tsar-Bomba test. So we don't really have any information past that because nobody's ever detonated anything bigger than that. But it should probably follow. This is I assume this is a fit to experimental data, a curve fit to that experimental data. So the bigger the cloud, right, and the higher the cloud, more it's going to spread out over a much larger area, and we're going to see more pronounced distribution of the fallout contained within the cloud. And this is kind of what so we've seen like that contour plot. This is what if we're really talking in terms of time, what's our cloud looking like? Well, let's start at something called TS. And this is the stabilization time of the cloud. This is when basically the cloud has gotten to the size it's going to be at the height that it's going to be, and it's now going to be affected by atmospheric conditions. So we'll call this the stabilized time, or TS. So what's going to happen? Well, if we look an hour after the stabilization of the cloud, we see that the lighter stuff, smaller particles, are still being retained within the cloud. The heavier stuff is starting to fall out. Hasn't quite hit the ground yet. If we look at 2 hours later, small particles, again, still being held within the cloud. The larger particles are now, between 1 hour and 2 hours, they're incident actually on the ground. And then if we look even further in time, we can see that as the cloud expands out due to, again, atmospheric conditions, that circle on the ground where our heavier material, our fallout is occurring, it starts to get out, spread out more, or smearing as it's called. And this produces those contours that we saw at the very beginning of the lecture. And then over time, our small particles, as our cloud starts to become less and less dense, they're going to start coming out as well, assuming they're not in a vapor state and aggregating. But this is still occurring as we move forward in time until finally we have no cloud. All of the material that's not vapor anymore is finally deposited on the ground. And so if you can imagine this circle changing, getting bigger, and then smaller towards the end, and then moving through the atmosphere as winds push it around, you can directly use these things to draw out a distribution contour map. It's pretty cool, actually. Okay, so that's going to be it for this lesson. In the next two lessons, we're going to look at, kind of as we did with prompt radiation, how do we characterize fallout? How do we characterize these delayed radiation sources coming from our nuclear detonation? And then what are we looking at for biologic effects?